Hi, good morning, everyone. Thank you very much to be able to be part of this program. I have the pleasure to introduce Brent Minchew. Brent was born and raised in Texas, and after serving 8 years in the US Marine Corps, he earned a Bachelor in Science and Master degree in Aerospace Engineering from the University of Texas, Austin, between 2008 and 2010. His PhD in geophysics was from Caltech in 2016, and he was an NSF postdoctoral fellow at the British Antarctic Survey in Cambridge, UK, from 2016 to 18. Afterward, he joined the Department of Earth and Atmospheric Science and Planetary Sciences at MIT and is an assistant professor there. His research focuses on glaciers, ice sheets, and emphasizing the process governing sea level rise. He uses a combination of remote sensing observations, mathematical theory, and numerical models to study physics at fast-flowing glaciers with account for the large uncertainties and projections of sea level rise. Right.
Great, thank you very much. Is this headset working? Everybody can hear me okay? Everybody good? Great, because I like to walk around whenever I talk. So yeah, thanks for coming. It's really good to see a nice turnout of everybody. I had a chance to walk through the poster halls earlier, and there's a lot of really exciting research that's displayed on those posters out there, and I look forward to having the opportunity to talk to the folks who are heading up those posters, learn more about the various research that's going on within the MIT Portugal program. I'm also very happy to see a lot of new faces, and so I look forward to meeting many of you, having a chance to talk to you, and so forth during this meeting. So I'm honored to have the invitation to give the keynote address. This is, I think, really exciting stuff that we're working on. A lot of this is in collaboration with John, who was just up here talking before, and he may mention just some things that we're going to get to toward the end of this talk. But I want to zoom out a little bit and kind of think about the problems that we work on, the problems that we care a lot about within my research group, and a sort of growing concern within the earth science community, and then, of course, society writ large. And that's thinking about sea level rise, and specifically sea level rise in this century. So sea level rise over human timescales. That is, what sea level rise is going to be within the lifetime of people who are alive today. And we're going to talk specifically and focus in on kind of the education and innovation that's going on within MIT Portugal and within other related efforts to really drive forward research into the science and the adaptation to sea level rise as it comes up. So we're starting off with a plot we took from the latest IPCC report, so Intergovernmental Panel on Climate Change. This is the 6th assessment. It came out just a couple of years ago or so. And this is for sea level rise scenarios for the coming decades. So a couple things to note. Timescale here along the bottom. So we're going from about 1950 out to the year 2100. So just sea level rise really focusing on this century. And then over here, there's a relative sea level rise. This is relative to the year 1900 or so. Units are given in meters of sea level rise. What I want to call your attention to is kind of what's going on over here around the end of the century. So written here in these colored letters, these are kind of cryptic expressions, but they're basically giving different CO2 emission scenarios. So the bottom here is a scenario in which emissions peak relatively soon, and then they drop off quite sharply. The red here labels 8.5. Typically labeled as business as usual scenario, as we continue with CO2 emissions more or less at the current rate, or they grow slowly over time. And then we'll talk about this dash line here in just a little bit. But one key point to note on this, in particular thinking about sea level rise, is this best case scenario emissions that we get from the IPCC still gives us a relatively considerable increase in sea levels out to the end of the century. In other words, glaciers and ice sheets, which are the primary source of sea level rise going forward, have a lot of memory to them. And so, in essence, a significant portion of the sea level rise that we can expect in the coming century is a consequence of what has taken place in the past century, and it's fairly locked in. But we have options. We have choices that we can make, and so forth, in terms of the overall magnitude of sea level rise within this century, in terms of how we deal with emissions, how we deal with sustainable energy, and this kind of thing. Now, bringing your attention back to this dash line. This dash line is basically an attempt by the authors of the IPCC report to represent the things that we know that we don't know about what's going on within the ice sheets, the instability mechanisms within the ice sheets, the rapid collapse of some of the vulnerable sectors of the ice sheets that we'll talk about here in a little bit, and the speeding up of the ice and increase in ice mass loss. This dashed line actually represents a relatively conservative view of what we think of as the worst case scenario. A lot of people in my field, myself included, would argue that this line should actually be a little bit higher because of these various scenarios that we'll talk about, a few of which we'll talk about in a little bit. But this basically gives us some sense of the spread, the uncertainties in our projections. In essence, our projections of sea level rise out to the end of the century are going to range somewhere between about 20 centimeters above present to about 2 meters above present. And those are very, very different scenarios. Right? Most places can relatively easily adapt to an increase in global sea level of 20 centimeters, 2 meters, almost certainly going to be catastrophic. To show you what that looks like from a practical perspective, many of you here are from MIT, or many of you have at least been to MIT, so this is what it looks like in our local neighborhood between the high-end projections and the low-end projections. So what we're showing here is maps of the Boston area. The MIT campus is located right down around here, with the famous dome located right around in there. So under low-end scenarios, MIT in this area, we're fine. We can build dams, we can build coastal barriers, we can deal with things, we're going to deal with increased levels of nuisance flooding and so forth, but overall, everything's going to be fine. Under the worst case scenarios, though, these blue areas are showing places that are underwater at mean sea level. So these are places that are effectively lost to sea level going forward under these worst case scenarios. And again, that's just at the end of the century. So as I like to put it, it's basically, for those of us who work at MIT, the difference between this outcome and this outcome is the difference between walking to work and swimming to work, basically. Okay? And this is repeated kind of all over the world. In Portugal, the impact of sea level rise is going to be a little bit different, as most of your shorelines have a relatively steep gradient. But sea level rise will impact rates of coastal flooding. It will impact fisheries. This is a lagoon out here and so forth. It will impact the potential for groundwater resources to be contaminated by seawater as it comes in. So many, many impacts beyond the simple inundation. At the global scale, the global consequences, the difference between the low-end projections and the high-end projections are huge. Many trillions of dollars worth of infrastructure difference in responding to the low-end projections versus the high-end projections. So this is basically the difference. The low-end projections build coastal barriers. In general, we're fine. High-end projections, cities like Miami are lost. Large areas of Bangladesh are lost. They're under sea level, right? So this results in basically the inundation of about 100 million homes. About 1 billion climate refugees, somewhere around in there, between these two scenarios. So we might want to know, we might want to have a pretty good idea of which one of these outcomes is more likely. Which one of these things are we heading towards? Because we're only a few decades away. We don't have a whole lot of time to deal with this kind of thing, especially if we're talking about mass movements of people, radical changes to society, and so forth. So when we think about these uncertainties and we think about this particular spread, then we can start to think about the sources, the physical mechanisms that are going to drive, that are going to make the difference between the low end and the high end projections. And pretty much all of those things end up living in one small geographic region, this particular sector of West Antarctica. So these are areas, there's a glacier there known as Thwaites Glacier. If you read the news, you may have heard about this thing. It's often termed the Doomsday Glacier and so forth, because everything has to be extreme language in the time that we live in. But basically, this particular sector of West Antarctica drives the vast majority of this uncertainty. And there's a list, not too long of a list, of physical mechanisms that give rise to these pieces. That is the instability of this sector of Antarctica. Now, when we talk about West Antarctica, you can see a movie showing here. You can see seasonal ice changes and so forth, but we're really going to focus in on this particular area. So you're starting to see these lines show up. This gives you a sense of the flow. These are the big glaciers. This is Thwaites Glacier, again, the thing that's often termed the Doomsday Glacier. This is another glacier called Pine Island Glacier. And if we're going to get 2 meters of sea level rise, then it has to come from this area. It pretty much can't come from anywhere else. The reason for that has to do with the topography beneath the ice sheet. So go ahead and, for the movie, pause it right there, please. Perfect. So in this particular area, this portion of West Antarctica, unlike East Antarctica, which is out here, which is a large ice sheet that's sitting on the continent, West Antarctica is basically an archipelago, a series of islands that's filled in with ice. So the bed of West Antarctica is about 2 kilometers or so below sea level. If we remove the ice sheet, we just get open ocean to about 2 kilometers depth or so. And because ice floats, then there are buoyancy-driven feedbacks that occur in this area in pretty much this area only, that can give rise to very, very rapid rates of ice mass loss and therefore sea level rise. So why doesn't this happen? Why isn't it happening right now? Why do we even have a West Antarctic ice sheet? Why hasn't it gone away? Basically because we have this last line of defense, a thing that's working in our favor right now. And this is the floating extension of the ice sheet. So the ice sheets you can think of, it's like forming a big puddle of honey or syrup on your plate and watching it spread out. Ice is just a viscous fluid over the time scales of interest. And as it spreads out, as it flows out, of course, it starts to thin, and since the bed here is below sea level, then if it thins enough, it starts to float. And these floating sections of the ice sheet are known as the ice shelves. These are the areas that are colored in right here, and these are one of the primary controls on rates of sea level rise. They are the thing that is stabilizing these portions of West Antarctica and preventing it from contributing to sea level rise at the moment. The reason for that has to do with this color map that we're showing here. It has to do with the resistive forces that are provided by these floating bits. So they flow out onto the sea, they start to float on the ocean. The ocean provides no meaningful resistance, but they do connect with the solid Earth. They do come into contact with sea mountains, island chains, and so forth, and therefore provide some resistance to the flow of the glacier toward the ocean. We typically refer to this as a buttressing stress, but it's simply a resistive force, a thing that is holding the ice sheet back, allowing it to stay thick enough that it is still in contact with the bed, with the solid Earth, so that most of the mass of the ice, or a good portion of the mass of the ice in this area, is still supported by the solid Earth itself, still supported by land. If we lose these ice sheets, then what we'll see is a significant rate of retreat, a radical increase in the rates of sea level rise. And losing the ice shelves is kind of something that we're watching going on right now. So these are satellite images of one particular part of Antarctica, and what you can see are these large-scale fractures forming. I'll call your attention to the scale bar down here. This is 30 kilometers. So these whole little pieces are significant. These fractures are 100, 150 kilometers long in some cases. And they form over relatively short time scales. You can see the date ticking away in the top for these different radar images that are showing here. So you can see this piece flowing forward. It's relatively coherent. You see a large fracture start to form here. Another one just kind of comes out of nowhere and calves off an iceberg that's roughly the size of northern Portugal, somewhere around in there. Okay? Big, big chunks of ice. These are about 200 to 300 meters thick, large volumes of ice that are breaking off. Now, since they're already floating in this particular area, then by themselves, they don't contribute anything to sea level rise. They've already contributed what they're going to contribute, but they have these resistances to the seaward flow. So as they break off, and if you watch really closely at the end, you'll start to see this thing kind of speed up. This is what's been going on in about the last 3 or 4 months as this situation develops. Okay? So all these pieces are breaking off. This area right here, if we zoom in on this particular sector, this is what I was talking about before. This is a seamount. This is where the ice is flowing off the continent. It's coming into contact with a mountain. It's grounded below sea level, and it's being smashed against that particular mountain. If you look very closely, you can see it buckling in these areas, but you can see all these fractures that are starting to form in this particular area. And you can see, as we get close to about a week or so ago, the most up-to-date observation, you can see all these pieces that are really starting to break off. This ice is losing contact with this particular sector, and thus it is losing its ability to resist the flow of the glaciers toward the ocean. Fun fact about my particular field, this is the key process. This is the thing that basically sets the rate of sea level rise in this particular century, and we don't know how to include it in our projections of sea level rise. That's why we have this dashed line, our best guess of what the worst case scenario might be, because we can't really include these processes within our current projections, okay? And that's due to our limited understanding of the relevant physics of this particular process. And our understanding of the physics of this process is limited primarily by our observational capability. What I mean by that is that while we get satellite observations that make really nice movies that I was showing before, it's not able to resolve things at scale that we need to resolve them. It's in terms of the spatial scale or the time scale. These things occur very rapidly in time, and they occur over relatively small scales in space. And we need to be able to zoom in on these things. We need to be able to localize them in both space and in time to be able to understand what mechanisms are driving this process, what mechanisms are resisting this process, what are the mechanical properties of the ice that give rise to the fracturing of the ice and the rapid break-off and so forth. To do all that, we need much better resolution than what we have available to us. So to help solve that problem,
we have identified a wealth of natural warning signs we can use to monitor and forecast major climate risk. To gain the necessary lead time to successfully react, they require more persistent and higher fidelity tracking than current technologies provide. Emerging from a collaboration between the MIT Schools of Science and Engineering, Harvard University, and MIT Lincoln Laboratory, the Stratospheric Airborne Climate Observatory System, or SACOS, is an unprecedented aerial observatory centered on an ensemble of high-endurance solar-powered aircraft. Capable of remaining airborne for many weeks or months, these aircraft will operate scientific missions with immeasurable benefits to life on Earth. SACOS offers key advantages over satellite systems by virtue of 4 factors. 100% of time is focused on the target, with the trajectory set specifically by what the onboard instruments require. A reduction in over-the-ground velocity from 8,000 meters per second to 30 meters per second. The elimination of ionospheric interference, and a reduction in distance to target from 500 kilometers to just 20 kilometers. Student teams have spent several years researching and developing feasible aircraft designs and missions. They found that summer months are ideal for SACOS operations when many critical climate change phenomena are active. The shorter nights require a smaller overnight battery, allowing for a smaller aircraft. We've designed a number of initial missions where SACOS could provide significant improvements in climate risk forecasting. For example, giant fissures create massive icebergs causing the Antarctic ice sheet to flow more rapidly into the ocean, raising sea levels around the world and threatening the displacement of millions of people. Current sea level forecasts are inaccurate because they struggle to account for these fissures. We will track the ice sheet fissures to accurately forecast ice slippage and give impacted populations enough time to prepare or evacuate. Widespread droughts are causing rampant wildfires and water shortages. SACOS aims to monitor soil moisture and humidity in critically dry regions to accurately predict where and when wildfires and droughts are imminent. Increasingly severe summer thunderstorms over North America penetrate into the stratosphere, injecting water vapor that triggers catalytic active free radicals that then attack stratospheric ozone. SACOS offers the best method to measure these free radicals to track and predict this localized ozone depletion. These missions and many more will yield clear, unignorable evidence of critical climate events that will disrupt and displace civilization. Our observations hold the potential to inform and predict so we can effectively and successfully prepare for what's to come.
So that's a fun movie for a very interesting project that we're going forward. As John mentioned before, and we'll mention now, and thinking about the future going forward, and thinking about how we understand rates of sea level rise, again, within human lifetimes. Okay? So I would argue that this kind of observation is basically the future of climate science. It's the future of understanding sea level rise. It's the future of understanding wildfires, changes in climate, and so forth. Many, many applications that we can use this particular airborne platform for. All right? But in essence, at least as far as I'm concerned, it's thinking about sea level rise, what this kind of platform does, this high altitude platform, it's going to fly in the stratosphere, it's going to collect observations, it can fly for months at a time, collecting continuous observations, and therefore it fills this critical gap in Earth observations. That is, this critical gap at the moment is that data are simply not collected often enough, and they're entirely too coarse in terms of their spatial resolution. A lot of the problems that we're interested in, thinking about sea level rise, thinking about geophysics in general, have certain characteristics to them. Right? They have a separation of scales. What happens at the small spatial scales impacts what's going on at the large spatial scales. And if you really want to know what's going on, you need to be able to resolve those relatively small spatial scales. They also share in common characteristics. If you think about earthquakes, this is a perfect example of this, very episodic type of events. Fracturing of ice is the same sort of way. That is, that there are long periods of relative quiescence where nothing terribly interesting is happening. And then everything interesting happens all at once over a relatively short time scale. And so the only way to be able to see these things, the only way to be able to observe what's going on, the only way to really be able to capture an iceberg breaking off, a rupturing of tectonic plates, a volcano erupting, these kinds of things, is to observe it constantly with relatively short repeat times between your observations. Sometimes you can decimate the data in periods where there's nothing interesting happening, but whenever something interesting does happen, you're able to capture these observations, grab them, use them to understand the physics of the system that's really driving these events. And so these more frequent observations, I would argue, is absolutely the key. This is the future of geophysics in general. This is the future of climate science. It's the future of sustainability, environmental research, and so forth. So more frequent observations will provide us with the information that we need to make rapid progress on important problems. Learn physics from data, this kind of thing. These platforms will provide for that. So in essence, what SACOS is going to do for us is it's going to fly for months at a time, which is totally unprecedented. Only satellites can stay up for a long period of time right now, but satellites have to orbit. They're wedded to their orbits. There are certain restrictions that cause satellites to not be available all the time. So the satellite observations that you saw before of the icebergs fracturing off and so forth, those are collected every 6 days, if we're lucky. There are 2 satellites. Recently, one of those satellites died, so now we're down to repeat times of 12 days or so. With this platform, we can get down to repeat times of an hour, less than an hour, this kind of thing, right? Fundamentally changes, order of magnitude improvement in the timescales or the temporal resolution of our observations. And we can do this with much, much finer spatial resolution, right? Much better than what satellites provide. Order of magnitude or so improvement in the spatial resolution, right? And so in essence, in summary, this basically allows scientists to collect the data that we need. Where, when, how often, and so forth. It gives us the flexibility that we need that satellites can never, ever provide. And we can do this, importantly, with flexible flight plans. Again, satellites have to stay in an orbit. So if we want to observe the poles, we have to be in a polar orbit, which basically means north-south trajectories in the satellites, right? We can't really fly east-west. It's just not the way physics works. But with SACOS and platforms like this, we can fly any direction we want. So we can optimize our look angle. We can look at things from different vantage points. We can see it from different points of view than what we can get with any current observations. And that will fundamentally change our understanding, of course, because anytime we're able to look at things from a different point of view, we learn a lot of new stuff. An important point to this, in terms of thinking about the conference, and hopefully something that seeds conversations going forward, is that this kind of thing really emerges from collaborations that are enabled by the MIT Portugal program. Okay? John was one of the main people that took the lead on this. And as he mentioned before, there were a number of students from Portuguese universities that played essential roles in the design and the development of SACOS, right? Many students from Portuguese universities were involved in the design class. They pushed forward, made important contributions to this. And again, pushed forward on this design that has now been turned into an actual physical aircraft. This thing is being built. It's ready to fly, hopefully, in the next few years, right? And so we'll be able to start collecting these observations in the relative near term so that we can start learning physics from data, so that we can dramatically improve our projections of sea level rise as they go forward, okay? And basically, again, so hammered on before, that's because this sort of platform is going to allow us to observe on the scales that matter the most, that we cannot currently observe. So we'll really be able to zoom in on things like the fracturing of the ice, the development of icebergs and so forth. This is leading order control and rates of sea level rise. We'll be able to zoom in on these tips and look at the intensification of stresses around these areas that cause fractures to propagate, that cause the material to pull apart and break off in these large-scale icebergs. We'll be able to collect enough data with SACOS to plug into powerful machine learning algorithms and other things that will allow us to learn physics from data and basically accelerate the process of development of the models that we use in order to project sea level rise, so that hopefully, in the not too distant future, we're able to shrink these uncertainties, to really understand what's going on, to give people the information that they need in order to plan, invest, and move forward, so that we can hopefully all do a decent job of adapting over reasonable rates to what's going to happen in the future, so that we can move vulnerable populations away from areas that are going to be most affected. We can build smartly the infrastructure that we need to adapt to rising sea levels. And we can make reasonable investments. We don't want to waste trillions of dollars. We don't want to underspend when sea level is going to be too high, and so forth. So if we can push forward with instruments like SACOS, push forward with basic scientific research and the processes and the ice sheets, then hopefully we can shrink these uncertainties, or at the very least we can quantify these uncertainties, and we can tell you which one of these outcomes is more likely so that we can be prepared for the future that comes. That's all I have. Thanks.
Thank you, Brent, for an inspiring talk, and Rita for moderating the session.
Thank you, Brent. This kind of development in terms of technology and being able to increase the observations of the ocean, is it feasible to have more than one SACOS plane flying for research or even for just simple weather forecasting?
Oh yeah, I mean that's the dream, right? The dream is that you build this kind of platform and that it's relatively affordable, right? And so it's affordable enough that we can have lots of them operating. So different entities in the U.S., you know, we can think about agencies like NASA, even individual states, possibly even these kinds of things get down to affordable costs so that individual universities could own them potentially. But the idea is that you basically, you democratize this information. You have a lot of these different platforms that can fly around. They can carry a number of different sensors. They can fly in different locations, and they can just collect a lot of valuable data. For the kind of things that we do, you know, what we want is to take these platforms and we want to put radar on them. So the kind of radar that we were looking at in the satellite images, where we saw the icebergs breaking off and so forth, we want to do that kind of thing. But we want to observe much more frequently. We want to fly around relatively small areas and view them often and so forth. And that same kind of setup, that same instrument on the same platform could be used to monitor wildfires. It can be used to monitor slipping on tectonic faults, development of earthquakes, hazards. It can be used to monitor flooding. It can be used to assess damage following catastrophic events like earthquakes, landslides, volcanoes, and so forth. It can be used for lots and lots of different purposes. So ideally, we would have a number of these types of platforms that are around that can be applied to all of these different problems. And then extending beyond that, and there's no reason to limit the platform itself to a single type of instrument. You know, other people, I want radar, and I'm interested in that sort of thing, and I'm interested in photographs, optical imagery that we can collect from this. But there will be other scientists that are interested in infrared observations. There will be other scientists who are interested in collecting data within the stratosphere itself. So the people that want to understand temperature, pressure, wind speed, chemical composition of the stratosphere and so forth. They want to measure winds of the stratosphere. They want to measure upwelling. They want to measure the connection between the troposphere and the stratosphere and so forth. So many different types of observations, many different scientific fields can all benefit from this kind of thing. And so if we have a large number of platforms out there, then we can enable all of these advances across a number of different scientific fields.
That's very interesting. Is there any question from the... Yeah, please.
It's just a matter if it's 50 or 100 years earlier or later. So is there a path to not having this level?
So, yeah, so that's a good question, thanks. So your question is there a way to avoid some of the more concerning outcomes?
Well, I assume it's global temperature rise, right? If we get it fast enough, low enough, then it's not going to fracture all off. Otherwise, it seems like inevitable that we will have sea level rise, right?
Oh, so it is almost certainly inevitable that we're going to have sea level rise no matter what we do. That we're going to have some amount of sea level rise. Even if we were to take atmospheric temperatures and we were to dial them back to pre-industrial, it's just going to take a long time for the ice sheets to respond, right? They're very viscous fluids. They have kind of a long memory baked into them, right? So it would take a while if we were to be able to magically dial climate back to what it was, let's say 500 years ago or whatnot, and then hold that constant. It would still take at least a couple centuries or so for the ice sheets to return to an equilibrium, state that is in equilibrium with that particular climate, right? So once the domino is tipped, there's a certain amount of sea level rise that we are committed to going forward, and that there really isn't much that we can do about it. But that amount of sea level rise, as I mentioned before, is relatively small. So somewhere around our best estimates at the moment, around 20 centimeters or so. We'll probably avoid catastrophic loss of some of these floating sectors of the ice sheet and so forth. But going forward, thinking about different emission scenarios, increases in global temperatures and whatnot, if we increase a little bit, we have increased global temperatures a little bit, we have a fairly significant impact on the ice shelves. So what I didn't mention before, basically what's happening, the reason why the ice shelves are starting to fracture and break up at the moment is that they're being thinned quite dramatically. They're being thinned from the ocean side because the changes in the westerly winds that circulate around Antarctica are driving warm, deep water toward the ice sheet itself, right? And so that warm, deep water actually hasn't known anything directly about climate for a few thousand years. Its temperature is set by what the conditions were many thousands of years ago. It's currently being driven toward Antarctica at a much increased rate because the winds around around Antarctica have intensified due to warming of the atmosphere, due to climate change and so forth. And so the intensification of winds pumps this deep warm water toward the ice shelves themselves, starts to melt the underside of the ice shelves, and then because ice is fresh and fresh water is buoyant in salt water, then you create this very efficient pump that starts to pull more and more warm water toward it and so forth. And so that sort of mechanism is also not easy to shut off over relatively short time scales. Even if we were to dial back temperatures, it would still take some time for the winds to respond to that. But in addition to that, on the ice shelves themselves, there's the direct effect of warming of the atmosphere, right? So it's melting of the surface of the ice shelf. So you can think about what's going on right now between the ocean and the atmosphere is basically burning a candle at both ends. So the ice shelves are thinning at a relatively rapid rate, and something that concerns a lot of us is that the melting that takes place on the top of the ice shelves starts to form big lakes and so forth of meltwater. These big lakes are big weights on top of the ice shelves. So these lakes can drain. We watch these things happen over satellite observations, and with that, you get this radical rebound of the ice shelf itself that can break it up and they can break pieces apart. None of this we're able to model in any way. And so again, like the worst case scenarios I pointed out before, those are mostly just best guesses. They're considered by the IPCC, they're storylines. They're not things that we're able to capture in our models. So if we were able to stop the rate of warming of the atmosphere, if we were able to return atmospheric temperatures back down to something like pre-industrial, then we could almost certainly avoid these worst case scenarios that were talked about here. But we cannot avoid all sea level rise. We are committed to some extent to a certain amount. So hopefully that answers your question.
Doesn't make me happier, but yes.
Hi, Brent. Thank you very much for this wonderful presentation. So my question is a little bit based on what you have said, so that really this is a multidisciplinary effort. So, and it is clear that it is a multidisciplinary effort, for example, in climate change mitigation, of which we have a lot. So you have touched upon a very important thing, which is to understand how that impacts sea level rise. My question now is, I know that MIT, you have different efforts on climate change adaptation. This is much less studied, and you have raised the attention to this one. And I believe that in the near future, and I guess sooner than later, we need to engage social sciences. So adaptation, of course, is a different animal, I would say. And of course, people need to understand it, and much beyond economists. So even the social, the way you communicate this, the way you engage people without frightening them so they don't leave, don't sleep at night. So I would like to listen to your views on your experience at MIT, different programs that I know you have. So how do you see this unfolding? Because I think this is important to MIT Portugal as well, as it is, I would say, one of the major flagship programs that we have in which we call for multidisciplinarity.
Yeah, absolutely. So there are certainly a number of programs at MIT. I won't say that I have a tremendous amount of engagement with them at this particular point because I've only been there for a few years, and everything ramps up slowly over time. We have developed a number of proposals working with people who are social scientists who specialize in connections with communities who specialize in connecting with particularly vulnerable populations in cities and so forth, that do think a lot about urban planning, who think a lot about these large-scale problems of moving large numbers of people ahead of time. And so these kinds of projects are underway to some extent. As a scientist, I am not super engaged in these type of social science outcomes, and the reason for that is just that there are only so many hours in the day, and I haven't quite found the right combination of working times to deal with these things. But there are large-scale programs. There are U.S. government-sponsored programs. There are programs through large entities like the American Geophysical Union and so forth that represents all of the scientists that are working on these things to try to create a channel of communication from the scientists to social scientists to community organizers to folks of this nature to economists and so the full spectrum, and kind of get all these different people with all these different areas of expertise involved to find the right way to communicate with different communities and whatnot, to get the word out to the public, to get the word out to the scientific community, and kind of everything that lies between. As you can probably guess from my presentation, I feel most comfortable communicating with scientists and other folks that think in terms of plots and numbers and things of this nature. I am not the right spokesperson for any kind of public-facing engagement or community engagement and so forth, but there are many people that are. And so we do work actively with them, journalists, science communicators, again, urban planners, economists, civil engineers that are working on all these features. And so we're slowly building these things up. But as you point out, I mean, this is truly multidisciplinary, and connecting across these fields is difficult because everybody speaks a different language effectively. We think about the problem in very different ways. And so bridging these gaps is an exciting opportunity, but also challenging. And it just requires, I think, time and iterating on these matters. And hopefully we can find ways to accelerate this process of communication, develop these maybe centers and so forth where you bring a lot of people together with all these different areas of expertise and whatnot. But that's kind of my view on it at the moment, my very naive view. Again, I'm quite new to this. I think I've been a faculty member for 4 years, so this is where I'm at the moment. Ask me again in about 10 years. I might have a very different answer for you.
Okay. Carlos Bento from University of Coimbra. First, thank you very much for this inspiring presentation, for all the work that you are doing and your team. As it was said before, this shows to be a multidisciplinary project. Me being from the area of computer science, I was looking how you see the role of AI on this project. I was thinking one is obvious, is on the side of data analysis, but the other one that I was asking about is which can be the role of AI on defining the mission of the airplane. Mm-hmm. This is one question. A second one is more on the features, that is, which is the range of altitude that the airplane can go, or the implications on the batteries on this? Mm-hmm. Thank you.
Yeah, absolutely. So that's a great question. So the role of AI, of course, is manifold. There are lots of different opportunities. As you mentioned, there's the fairly obvious one in taking the data from the raw measurements. So for example, when we collect radar data, what we're really collecting are voltage measurements from a signal that's bounced back. And we want to be able to process these things. We need to be able to focus the radar data and so forth to make the images that we have here. And then we need to take these time series of images like the ones that you saw in this movie, and we need to turn them into displacement fields. We need to turn them into measurements of the rate of deformation and so forth, because that connects with stresses. And that's a relatively involved process. And we know how to do all of the steps basically, but it's very computationally expensive at the moment. And so bringing in AI methods has the potential to dramatically increase the efficiency of these computational algorithms so that we maybe don't contribute directly to sea level rise just by computing these things, right? The other way is in analyzing the data sets. So we have a number of projects that are just getting off the ground and thinking about things like physics-informed neural networks and so forth that do a really nice job of allowing us to infer properties, to infer physical mechanisms that are taking place from the observations themselves. And so that piece of work is going on. We're bringing in methods, variational inference, for those of you who know what that is a really efficient way to calculate the uncertainties in our observations. Because we always want to be able to apply uncertainties. We always want to be able to propagate errors through and give an uncertainty in the eventual outcome to our analysis. In addition to that, I think there was probably a third thing that I was going to say about the use of AI. I'll probably remember it in a little bit, and I'll let you know. But you asked a question, a practical question in terms of the observations, in terms of the altitude of the aircraft that's flying, if I remember correctly. And so typical altitudes of the aircraft, they're going to be in the stratosphere, so they're going to be above the troposphere, which is where we live, so they're going to be flying above the weather. So typical altitudes over the poles is going to be around 15, 18 kilometers, somewhere around in there, well above where commercial airliners fly. And then around the equator, where the troposphere is a little bit thicker, stratosphere is a little bit higher up, I think it's going to fly closer to like 20 to 22 kilometers, somewhere around in there. So again, way above the weather, which is nice for us. So you don't get much variability. Where there are winds up there, but the short-term variability in the wind, that is gusts and things of this nature, is relatively small. And so we should have a fairly stable platform that allows for the kind of precise observations that we want to make. Yeah, and once we're up there as well, I mean, of course, kind of one of the key advantages of being up there is that the density of the atmosphere is relatively low, and so the drag on the aircraft, the tendency to kick around the aircraft due to the winds, any kind of short-term variability is also relatively low, and so it should provide us with a stable platform. So I'll think in a little bit of what the third thing I was going to say about AI is, but there are just many, many possible applications of AI in this particular realm. Certainly many things that I have never thought of and that other people will think about going forward.
Hey, Brent, I'll jump in and help you because there is one other thing that's important in AI, which is the vehicles are in a place where you can't communicate with them very easily or very high bandwidth. So you need AI to actually, or some sort of automation, to look at the observations, figure out what are the important features that it's seeing, and actually modify the flight plan to track the features. So you can sort of give it seeds of what you might be worried about, but you're going to want the vehicle itself to be smart enough to go and focus on this thing that's interesting.
Yeah, absolutely. Yeah, thank you, John. That was the third thing. Yeah, adaptive sensing. You know, the ability to kind of tell the platform that you want to collect a certain observation with a certain level of error, and to let it kind of go out there and figure out what it needs to do in order to do that. That would be the ideal long-term future, so that we can optimize the observations and get the best and the most information that we can out of the time that we have. So thanks, John, for jumping in there. It's always the third thing that I forget. I should probably start with the most important thing first.
Hi, this is João Vilela from the University of Porto, here on your right.
There
you are, yeah. So thank you so much for the nice presentation. Looking at this now from a communications perspective, so how do you plan to have access to the data? Is when the plane lands, which may not be very interesting if it goes on for months, satellite communications, other sort of things?
So at the moment, we're kind of punting on that, and we're saying that kind of the easiest way to download the data is to land, probably swap out the disk array, download it, and so forth. But in the coming years, a lot of developments may be coming online that will sort of effectively solve this problem for us, essentially. So, you know, constellations of satellites like Starlink, that's flown by SpaceX and so forth, may give us high-speed internet access even within the polar regions that will allow us to ideally just put the data straight into the cloud, and we can start to use it right away. But at the moment, at least in the poles, there aren't too many options available to us that are affordable. you know, satellite communication uplink like Iridium and this sort of thing becomes prohibitively expensive. There are relatively few downlink stations that are available to us in the poles. So I think in the early phases of data collection, my guess is that we won't have much of a choice but to fly for essentially a length of time that is set by our onboard storage capacity of data, and then land, download, and fly back out again. And that's okay from a scientific perspective. It ends up being fine because the nominal airspeed of the platform gives us somewhere around sort of 2,200 to 2,500 kilometers per day or so. And so if we're interested in regions like Antarctica, the most vulnerable regions of Antarctica, for example, we could take off from New Zealand, the SACOS, and we can be in place, you know, within somewhere around 12 to 16 hours, something like that, and we can start collecting data. With the mass limitations and the power requirements, I think and the rate of data collected from the radar instrument itself, I think we could probably put enough solid state drives on board to store, let's say, 3 to 4 weeks worth of data collection or so. So that means that about every month we lose about a day or day and a half of observational time flying the aircraft back, landing it, swapping out the disks, and flying it back to where it's going. So 4 months of observations, basically with a loss of about 3 days worth of observations in between in order to fly and download the data and so forth. But going forward, and perhaps even at the low latitude areas that I don't work on, so I haven't thought a lot about in terms of data downlink, there may be ways to, there should be ways to transmit the data back to the ground, and so the aircraft can fly for long periods of time, even indefinitely in some areas, depending on where it's at. So data downlink will eventually become a very important consideration in the engineering, but for now, it's not very high on the list of priorities because it's not of significant cost at the moment to just land the aircraft, swap out disks, and send it right back up again.
All right, thank you.
And the sheer amount of data that you're looking at, you obviously need more than double the time that it takes to collect it, to analyze it.
Oh, yeah.
So a day itself will be more than a day to analyze all that data, just to download the data. So
certainly.
So losing 1 day in 3 months is not a very big loss.
It's not too bad.
It's not too bad. No.
That's right. That's right. Yeah, it'll take us a while to. People will be chewing on these kind of data sets for a while. I mean, what's interesting about a platform like SACOS is that in terms of bytes of data, it will collect more than we've ever really had before in a relatively short period of time. I mean, just the rate of observations, the rate of data collection, particularly in the poles, has increased exponentially just since I've been in the field. So when I was a PhD student, the first ever map of all of the flow speeds in Antarctica was published, and that was 2011. That was our first view. Our first actual view of the whole of Antarctica from satellite observations came in 2004. This is all relatively new things. And then over time, that map in 2011 that I mentioned before in terms of the flow speed of the glaciers, that was all of the data that had ever been collected, all aggregated together to make that single map. Now we've reached a period where we can make that map about every 2 months or so, going over and over again. SACOS will take that and increase the data haul by order of magnitude, somewhere around in there, but only in relatively small areas that we're going to focus on. We'll still let satellites give us the global coverage, and we'll let platforms like SACOS fill in the gaps.
I was a bit surprised about the very short amplitude of the signal on sea level rise, given that the amplitude on the atmosphere temperature is very large between those scenarios.
Yep.
So what do you think that could be the simplest way to increase that amplitude or get a more reasonable response from the ice sheets or from the models?
So increase the amplitude of sea level rise.
Increase the amplitude to, or reduce the uncertainty, basically.
Oh, reduce the uncertainty. Yeah, that is a challenging question. So the uncertainties and the spreads, there's always going to be a large range of uncertainties in dealing with a system like the ice sheets because they are, particularly the areas that we focused on, like West Antarctica, our current understanding of them is that they are potentially unstable. And anytime you introduce instabilities into the system, then you're always going to have a relatively large range of uncertainties, particularly when you're in the position like we are in the field and you don't actually have a particularly good way to model these uncertainties. And fortunately for society, unfortunate for science, we don't have any sort of observations to work off of, really. We've never seen the ice sheet go unstable before. We have observations from the paleo record, but they're quite crude in terms of their spatial, in terms of their temporal resolution and whatnot. So we're basically faced with a complex system that very likely has a number of instabilities in it, and that is entering a state that is way outside of anything that we have ever observed before. And so we're basically faced with the challenge of trying to extrapolate forward a potentially unstable system well outside of our calibration range, well outside of our observational range, and so forth. And that's always going to create a scenario where we have some fairly significant range of uncertainties. Ideally, we'd like to shrink these uncertainties, but I don't think we're going to should be able to shrink them by a significant amount. But what we can do a better job of, I think, is quantifying those uncertainties. So right now we have this range of possible outcomes of sea level rise, but we can't, as a field, really tell you which scenario is more likely. Are we more likely to get 20 centimeters of sea level rise, or are we more likely to get 2 meters of sea level rise? We would like to at least be able to assign a probability to these outcomes, and that's kind of the key. And I think the only way to do it is in over a reasonable time scale is through observations, observing these relatively high frequency events and trying to extrapolate those out to lower frequencies and the time scales that matter.
Yeah, I had a question.
Yeah, thank you. Doug Hart from MIT. I'm going to ask a very classic MIT question, which is, first of all, you presented a solution to a problem. SACOS is certainly measures at a high resolution, but it can't measure everything. And so the question one is, if you, as a climate scientist studying the instabilities of these things, if you could get data on anything, I mean, including what you can't see, what would be the key data point that you can get? And what can SACO do, but you presented very well, but what can't it do that you would really like to have?
Lots of things is the answer. Let me see, I think the main one, if I could collect a data set that doesn't currently exist and is probably beyond our capability to collect with an instrument like SACOS, with any remote sensing application, so forth, it would be to understand changes in the temperature and salinity of seawater within these areas that are coming into contact with Antarctica. So if we're thinking specifically about sea level rise, then that's really the kind of one of the things that really matters. But we can't, I don't think that we can even hope to observe that from remote sensing observations. I think that we have no choice but to send ships out in that area. And of course the reason for that is that the ocean's salty, and therefore it attenuates any kind of EM radiation that we may be able to observe with remote sensing. But that would be the thing that I would try to get. That would be the primary piece that I would try to focus in on. Again, very difficult measurements to take, very costly measurements and things that people are focused on and trying to get at. The additional piece, something that a platform like SACOS could conceivably do in future iterations, is get a better understanding of what the bed beneath the glaciers looks like, so that the topography of the bed and so forth is a key factor in setting rates of sea level rise in particular, if we're just focusing on the sea level rise question. So those bumps that you saw in the bed in the movie and so forth, those are key features, because it just so happens that ice sheets, because they're a viscous fluid, whenever they start to retreat, they tend to get stuck on these points, right? Their retreat tends to be episodic. And so really the timescales of sea level rise, or rates of sea level rise, are set by how bumpy the bed is. our current resolution of the bed topography, while it looks good and all in movies that are kind of at a continental scale, the actual resolution of it is about 15 kilometers in the best observed areas. And that's nowhere near good enough to really understand what's going on. So an observation that like SACOS could make would be to use much lower frequency radar than what we're using for these surface observations that can actually penetrate the ice and can return signals from the bed that we can then use to map out these features of the bedrock. But beyond that, yeah, there's a whole host of measurements, but that would be kind of the key feature. I'll return real quick to the challenge of measuring ocean melt rates. Well, one of the things that we can do with SACOS using these observations, just like we showed in the slides, in the movies of the ice shelves breaking up, we can use those observations to infer what the melt rates are that are caused by the ocean. So as long as we have very precise measurements of the speed of the ice, sort of horizontal plane, as well as the uplift of the ice and the vertical, we can use those observations then to infer how quickly the ice is melting off the base. We just combine these things with regional climate models that give us the rate of snowfall on the surface. We use the observations of speed, the bending, the profile of the bending of the ice shelf caused by the ocean tides, which gives us an estimate of what the thickness profile is, and then we just apply conservation of mass. And our main unknown variable then is the rate of melting off the bottom. So while we can't actually observe the changes in temperature within the ocean, we can observe the effect of those changes in temperature in terms of the melt rate of the ice itself. And if we're thinking about sea level rise, if we're thinking about processes of the ice shelves and the ice sheets, then that's what really matters, right, these changes. And so a platform like SACOS that gives us better resolution in time and in space will enable those kind of inferences to much higher quality than what we're able to do them right now. So there's a lot that we can kind of work on by taking these surface observations and applying them to what's going on. So.
Okay, Brent, we would like to thank you. We reached our time.
Okay.
Thank you very much. Thank you for listening. Thank you.